Yep.
It doesn't show.
Going now.
Okay.
Okay, so I guess we have quite a lot of viewers now, about 9 watching. So um, uh, let's quickly get started off with this. Girish, sir, you want to put yourself on unmute?
Hi, everyone.
Hey, good evening, everyone, and welcome to the ShaderLab Bootcamp series by Game Makers and ShaderShorts. So, as we had discussed earlier, this is a very basic series or a boot camp where we are going to learn the basics of graphics programming, the pipeline, and we are going to have a little bit of a live programming or coding session. So, a few of you might be knowing me. My name is Videep, and at present I'm working as a tech lead at Honeywell. I have worked in a couple of domains like architecture, sports, films, and now I have gotten into industrial application development. So that's quite about me, and I'm pretty much passionate about graphics and computer programming. With me here is Girish Sarwal, and he has been a mentor to me. We have worked very closely. Uh, to say a few words about Girish, I would say Girish has been, actively involved with his startup, Glue Tomatoes Gaming Studios, for about 5 years now. He also runs the meetup group called Game Makers. So if you must have attended the meetup group and RSVP'd for it, that's the Game Makers meetup group. Over the past 1.5 years, half decade basically, he has worked with core graphic technologies such as DirectX and OpenGL. And also, he has been writing for VR based technologies such as Oculus Rift and Vive. Okay, he is also an avid electronics and hardware guy, to be very honest. I mean, if you see his blogs and his YouTube channels, and if you follow him on Twitter, you would definitely see a lot of hardware programming and a lot of electronics thing going on. So he's like overall into graphics, hardware, and a lot of computer technologies, to be very honest, the proper tech person. So he'll be talking about core graphics concepts today and getting us started in the basics of game rendering. All right. So I would like to pass over the mic to Girish Sarwal. Girish sir, to you.
Thank you, Videep. Thanks a lot. And thank you, everyone, for taking out time on a weekend. Sorry we had to do this on a weekend, but given that it's Corona, I think weekends and weekdays don't really make much of a difference. So thank you for being here. And I'm going to be talking a little bit about how do you get started with graphics, how do you get started with rendering, I'm sure there must be there must be people in the audience coming in from diverse backgrounds. Some of you might already have some kind of exposure with graphics. Some of you might have written shaders earlier. Some of you might be some of you might be totally new to how graphics are done. So I'll try to do justice to this talk, and I'll try to ensure that I'm able to get you guys started with graphics. So Videep has already given a nice introduction about myself and himself. But in any case, anybody of you wants to catch up with us or huddle with us over other channels, then you might want to take a note of our emails or our LinkedIn profiles, our Twitter handles, etc. So without further delay, let's just get into it. And before we do that, I just wanted to set some expectations correctly. I just wanted to ensure that we're all on the same pace before we start learning about new things. So I actually went up and made a slide that talks about, what are the expectations that we are going to be setting up today. So please allow me a little bit of leeway here. There's a slight delay in my video transmission. So, yep. So here we have the slide. So when we talk about graphics, when we talk about drawing anything, or when we talk about putting anything on the screen, that includes things like mouse pointers, or buttons, or standard UI elements versus stuff like images, or stuff like real-time frames, etc. We end up doing a lot of drawing and a lot of painting. So essentially everything that you see on your screen right now, including the text that you see on your screen right now, is getting painted in real time. So there is the computer display does not really understand what an S is, or what a E is, or what a 0, 1 is. It just sees pixels. All it is doing, it is drawing one on top of another. And colloquially, we call this the painter's algorithm. It's very simple. That typically says that drawing happens in layers. So you paint a layer, and then you paint that layer with another layer using another color. The second thing that I really want to bring to the table before we really get into writing for graphics is that whenever we're writing games, or whenever we are writing any real-time paradigm or any real-time program, there is something known as the infinite loop. The infinite loop essentially means that we're always processing. Now, this might come up as a surprise for people coming in from ID backgrounds, that we always have an event, and you handle an event, and then you process things on that event, and things are hunky-dory. But when you're writing games, you're essentially always processing. So when I say always processing, you start by calculating a lot of stuff, and you slam it on the screen. Then while that gets slammed on the screen and that gets shown in the front, you're anyways doing more calculations and then slamming something else on the screen. And this gives us the illusion of animation. So essentially, there is one function that keeps on getting called over and over again, and we like to call it the infinite loop. The third thing that we really should be setting our expectations when we are talking about the contemporary game programming is that we want everything to be done by the GPU. So we want to offload as much as we want to the GPU. Whatever we can't do on the GPU, we do it on the CPU. So these are three basic rules that we want to keep in mind before we start further. So at this point, I'll just quickly switch gears a little bit, and we'll go down to the very basics of how you see things on the screen, and that essentially is done using a display. So if you look at the slide, there are two pictures on my screen. One of them is from a information system, and the another one is from a game. So when we talk about graphical user interfaces, or even character user interfaces like one you have on Linux, or on a terminal, everything is drawn. Everything you see is an image. That image is typically calculated at runtime. So if you look at the game on the screen, that is essentially an image that is being generated at runtime. How does it get generated? We are going to be talking about that later in our further slides. But as of now, we just want to understand that everything that I see on the screen is being drawn. So you have to step into the role of a painter, and you have to start painting things on the screen. And that's one basic change in thought of process that we have to accept when we start writing for games. with games, everything essentially is drawn in real time. So you're always drawing, you're always calculating, you're always drawing, you're always calculating, and you keep on doing this in a loop. And that was the premise of our second uh, assumption that we made when we started our thing. Now, to understand how drawing happens on the screen, we really need to understand the concept of what a display looks like, or what is a display. So essentially, a display could be your television, it could be your monitor, it could be a banner that you see on the road. So we see a lot of displays in our life every day. Now, essentially, what is a display? And the way I like to put it is that a display is nothing but an array of, or a 2D array of pixels. What is a pixel? A pixel is a short form for a picture element. So think of pixels as bulbs. Think of pixels as LEDs in your, you could really think of, when you're looking at your TV screen or your monitor, you should just think that you're staring at a big array of bulbs that are going row wise, and that are going column wise. And the product of these two is essentially what we call a screen resolution. So when I say that my screen is 4K UHD, or when I say my screen is full HD, that essentially means that I have, my computer monitor has 1920 bulbs. It is 1920 bulbs wide and 1080 bulbs high. So when I do that multiplication, I get to a resolution which I colloquially call as a HD resolution. So the bottom line here is that when you look at a display, I like to think of it, just think that you're staring at an array of bulbs, and our job really is to ensure that how do we actually turn these bulbs on or off. So for instance, if you look at the bottom left pixel in this slide, then all the pixels are on, and there is only one pixel which is colored black, which is off. So essentially what you see is that you see a square with one corner that's not lighted up. So let's actually figure out how. Now we understand the theory behind a display. A display is just an array of bulbs, and we turn them on or off. And then let's actually figure out how these displays used to show images. So here is a small display. Bear with me; it might take a minute to come up. And here is a small display, and in this display, you would see the words GL. So when you see the words GL, essentially there are some pixels that are on, and there are some pixels that are off. So based on turning these pixels on or off, we can actually combine them together, and we can start seeing images on the screen. Essentially, in this particular case, when a lot of pixels are on at a certain point in time, that is something that we typically call a frame. Or for example, at this point, whatever you see on the screen is a frame. Now, if any one of these pixels turned off, then that would be another frame. And let us say, we had all the pixels turning off, that would still be another frame. So the state of these pixels at any instance is typically what we call frame. Now, why do we want to talk about frame here? Because frame is something that you would typically hear in the graphics programming language every now and then. So, people are going to come and say, all right, how's the frame buffer looking right now? How many frames per second are we presenting? So essentially, when somebody says that we're running at 30 FPS, which means that I'm actually changing the state of that frame 30 times in a second. And that gives me the effect or the illusion of animation. So if you really look at a video editor, I mean, if you would have looked at a video editor at any point in your time, you would see that there is a small timeline at the bottom. Generally, if you work with things like Illustrator or After Effects or any other video editor for that matter, you would see that there is a timeline at the bottom, and that timeline essentially is showing you pictures which are stitched in a sequence. Now, as you keep on flipping those pictures around, you start seeing the effect of animation, which we typically call as a video. Now, so when so in this particular case, the state of pixels at any instance is typically what we call a frame. and the memory representation of how this frame looks like in your computer or in your RAM is the frame buffer. So these are just technical terms that you might want to know at this point in time, because when Videep starts his coding, I'm sure everybody, we would want everyone to follow what's happening. So every time the state changes, the frame buffer refreshes, and our job here is to keep on refreshing the frame buffer. When that happens, you would see that you would actually notice an animation. So, for instance, if you look at this particular slide, I don't know how many of you noticed, but something moved on this slide, and what really moved was the actual letters GL actually changed their place. So they moved around. So if I go back to the original slide, then I come back to this. Let me do this a couple of times, and you'll be able to appreciate what's happening on the screen. So when we're writing for games, essentially what we're doing is we're just changing the state of this frame buffer, and we keep on changing the state over and over again, and we keep on writing to this frame buffer over and over again. And when we do this, when that happens in a sequence, what you see is an animation. What you see is something known as a procedural animation. And this procedural animation is the basis of all games, all graphical animations that happen across the board. Whether you're doing animation, whether you're moving a model on the screen, whether you're doing something in Max or Maya or Blender, or you're writing a game, or as simple as you're watching a movie on the screen. All of this is in fact nothing but changing the frame buffer continuously and then stitching it together. So essentially, animation is, when things move around or they jump around or they're inflating, deflating, you see a collision on the screen. Animation essentially is mathematics, and animation essentially is computing. So our job as game developers is essentially to figure out how this mathematics works and to figure out how this computing works. Once we're able to do this, trust me, we can create any kind of animation that we wish to. Now, a core concept here also is that when this animation happens, I mean, if you really had a frame buffer on the screen, or if the display was lighting up some bulbs and you were seeing something on the screen, and right at that point you turned off one of those bulbs, what would really happen is that you might get an effect wherein half of the frame buffer would have been changed and the rest wouldn't have been, which can lead to some artifacts on the screen. So essentially what we do here is that we typically have two buffers. One of them is known as the front buffer, one of them is known as the back buffer. So whatever is on the front buffer is seen on the screen, and while it is being shown on the screen, we write to the back buffer. This technique is really a 30-year-old technique, and we typically call it double buffering or multi-buffering. And then there is something on the swap chain that's responsible for swapping these two buffers back and forth. So really, our takeaways from this entire thing is that, the first thing that we'll need to understand is that images are essentially nothing but 2D arrays represented in a contiguous memory location, which we lovingly call a frame. Displays are nothing but light sources that turn on and off based on a 2D frame in memory. So you have multiple 2D frames in memory, and there is a component in your system that's responsible for flipping them around. But all you're doing is that you're writing to that 2D frame, and that 2D frame gets slammed on the front, and then another 2D frame gets slammed on the front, and that's how animation happens. So we are really changing the 2D frame all the time, which is also known as an animation. In short, we're always computing, and that's the reason for the infinite loop, because we need to keep on computing over and over and over and over again. Now this change happens instantaneously, essentially because we have a buffer with us, and we always try to keep on writing to that frame buffer. The good part is that all of this today is done under the hood by most gaming engines, most UI frameworks. So essentially, when you're making a game with Unity, all of this is being done for you in the background. However, it is good to know that things work like that, because that kind of gives you an understanding of what's happening under the hood. You don't really have to worry about how to wire this up. I mean, if somebody's really interested, there are lots of resources available on the internet that will tell you how to wire up a double buffer, etc. At the same time, if you're working with core technologies like DirectX or OpenGL or Vulkan, you have to do all of this yourself. But if you're working with gaming engines like Unreal or Unity, then all of this is it's part of the package. So all you have to do is you just have to set some things in the correct place, and all of this happens automatically. So from here on, we have figured out a little bit about how displays work, and now we're going to be talking about we're going to slightly switch gears, and we're going to jump directly into what 3D is essentially for us. So I'm sure a lot of people in the audience would be coming in from 3D backgrounds, and they would be they would have worked with 3D in the past. You might have used things like Blender, you might have used things like AutoCAD programs, etc. But essentially, I talk to a lot of people, and typically I get this question a number of times: that does 3D really exist? I mean, everybody tells us that 3D is just 2D on the screen and done in a special way, but do 3D things actually exist, or do 3D structures actually exist inside a computer? So my answer typically to them is that yes, 3D things do exist. They typically only exist as a set of numbers. So there is no manifestation. I mean, memory is not 3D. Memory is typically 1D. So memory is just contiguous array. It's a contiguous array of 1D array of bytes. So how does 3D come into the picture? Essentially, everything that we talk about, when we talk about a model in 3D, when we talk about when we talk about seeing things in 3D, what you have to understand is that every point in that 3D is essentially stored into the system as a vector, or as a you could have lots of you could have lots of data points in a cloud that actually form up that entire object, and these are so 3D points essentially actually exist as matrices. Now, some of you might say that they don't exist as matrices; they exist as numbers. But the reason why I say they exist as matrices is because if you look at the basic vector form of how a 3D vertex is stored, then it is stored as a matrix inside your RAM. So you essentially have 3 floats in a line or 4 floats in a line that will actually represent a vector. So which is why I believe that it is stored as a matrix. Now, there could be a lot of other information about a 3D object that can be stored. So you could have a vector, you could have the position, you could have you could have something known as a vertex. A vertex essentially is a corner of any 3D object that you see. So you could have the color information, you could have the normal information, etc., that gets stored with a 3D object. So 3D object essentially is nothing but, it doesn't really have a physical existence inside the computer, but it's a set of mathematical points, or it's a set of vertices that get stored inside the computer. Now, I pulled up some basic meshes from the internet just to illustrate the concept. So if you look at this slide, you would see that there are a number of images there, and let's go over them one by one. So the first one is essentially a cube, and a cube made up of cubes. So you see there are a lot of dots in that cube, and those dots essentially are the vertices. So those are actually that is actually information of where one of the item exists in the 3D space. The second graphic that I really pulled up was to highlight how the number of vertices inside every 3D object really dictates as to what the end quality of that image is going to look like. So there are 4 bunnies in this particular image, and you would see that the first bunny has very rough edges. It's very geometrical in shape, but as we move across all of those bunnies, you would see that the last one has a lot of well-defined curves, well-defined organic surfaces. And the third image that I really picked up was for a humanoid form, and this was only to illustrate essentially that in a particular model you could actually end up having lots of vertices to define it. And one of the primary goals of us as game developers is to find a perfect fit of what can really help us get good frame rates on the screen. But before we do that, let's there are some other facts that we need to really figure out. The first thing that we need to figure out, which we can see in all of these images, is that you would see a lot of triangles in this entire model. So what you might see as a curved surface is actually always formed up of triangles, or at best a quad. Now, why do we need a triangle to define that? Because a triangle is the smallest unit which can define a plane. So if you look at any body, or if you look at any 3D object in this world, for example, if you look at this cup, then this cup is made up of surfaces, and a surface can essentially be defined by a plane. Now, a set of these planes can actually define the complete hull or the complete mesh of a surface. And we use a triangle because a triangle is the basic building block of a plane. A triangle is the smallest unit of a smallest polygon which can actually define a plane in its form. You can't do that with 2 points, and if you think about 4 points, then you can already define 2 triangles inside that. So which is why we treat everything as a triangle. And if any one of you has ever gone out to buy a graphics card, you would realize that they are typically sold by something known as a tessellation rate, or the number of triangles that it can process in a second. So which essentially defines the capability of a graphics card. Now, making these triangles by hand can be very difficult, and can be a very complicated process. You need to have a it's a common fact that people who are artists are really not inclined towards doing a lot of maths, and people who are completely into sciences, they're not very inclined towards doing art. So essentially, programs like Maya, Max, and Blender allow us to create these meshes or create these objects at in a wide-swing manner. So an artist typically opens up Max, and he draws. The artist actually draws, but what comes out of that program, the file that comes out of that program, is nothing but a long list of triangles that game programmers typically use to game programmers consume to load up things on the screen. As game programmers, our job really is to bash all these triangles together to draw these vertices on the screen. And the way it happens is using the graphics pipeline. We'll come to that in a moment. So 3D essentially, when you see this cube on the screen, there are a lot of 3D points in here. Your job is to bash these triangles together and convert them into pixels. Once you convert them into pixels, you can really slam it to the frame buffer. The moment you slam it to the frame buffer, you start seeing things on the screen. So which is why we always say 3D is virtual and it realized by 2D drawings. So our problem statement as game developers essentially is, I've got a cube, and these 3D coordinates are in my head, or they are mathematical calculations, and my job is to convert it into these array of bulbs that I can light up or or turn them off. And the moment I do this, I start seeing images on my screen. So in this particular slide, you can see a very rudimentary image of a cube. Imagine if you had bulbs laid out like this, you could easily draw up a cube by lighting them or turning them off. So we as developers, our primary responsibility is to convert this set of coordinates into these 2D pixels that we can light up. So another takeaway slide. The first thing that we understand that 3D content is just mathematical information that we are responsible to convert into 2D images on the screen. Takeaway 2 is that triangles are basic building blocks. Meshes are big lists of triangles. Takeaway 3 from this is that we need to smartly use the CPU and GPU to convert our big lists into pixels. And when I say big list, these can be really big lists. You could have thousands or even millions of triangles. And I remember, about a couple of years back, about a few years back, I and Videep were actually doing this thing together, wherein we were trying to reduce the number of triangles that were on the screen. So you could really easily run into millions. Imagine a small object that has about 1,000 triangles on the screen, and you want to instantiate 1,000 of those objects. You easily reach a million. So it's our job as a programmer to effectively and to very smartly utilize the CPU and the GPU to do our conversion. So again, for the purpose of our convenience, most game engines available today have all of these algorithms built in. We do have to do a little bit of work to wire things up together, and that would be one of our discussion points in today's meetup. All these engines know how to use the GPU for computationally expensive stuff. So our job essentially is to just advise the GPU or hint the GPU on how to do things, and then we just let it work on its own. Additionally, developers can also instruct the GPU or really hint the GPU on how to do this computation by writing very small programs called shaders, and that would be our point of discussion today. Now, shaders can also be very difficult to write. I mean, if anybody has worked with GLSL or HLSL shaders or core shaders, you would realize that they're not only difficult to write, they can be very difficult to debug as well. So at times you would run into a situation where you're not seeing things like you want them to, but you will end up with a very small bug somewhere which is very hard to trace. So shaders can be really overwhelming to write, and since there are so many types of graphics cards available and supporting different shader models, so it can often become very complex to ensure there is backward compatibility between shaders. So game engines typically provide us with their own compilers and interpreters. For example, Unity comes with ShaderLab, and Unreal comes with a node-based editor which you can use to wire up shaders together. So most of these game engines actually provide their own implementations of or their own wrappers around these shaders, which help us write them effectively. So this is the final part of my presentation before Videep kicks in and he gives you a hand at writing shaders for real. So before we actually talk about how 3D gets converted into 2D, it's important to really understand that, like we said, 3D in itself is just a set of points in 3D space, and we have the responsibility of converting them into pixels. We need to understand a couple of concepts as to how does that set of 3D points get converted into those 2D points. Typically, all of this will be done for you by game engines, but it's always good to understand how these things work, because when you write shaders, you typically have to deviate from what the game engine is doing by default, and you have to provide those implementations yourself. So what really differentiates 2D from 3D content is 3D always has a depth or a view. Every 3D object typically has a depth, whereas 2D objects don't have a depth. That's the definition we've been made to believe since day one. And when we have depth, the big thing about depth is that you could actually change the view around the depth. So for instance, if there is a particular object, or if there is a particular rectangle, when you're looking at a 2D rectangle, you can't really go behind the rectangle and have a look at it. But when you're looking at a 3D object like a teapot on the screen, you might have different views for it. You could be looking at that object from the front, from the right, from the top, from the left, or from any arbitrary angle. So we really need to, as programmers, we really need to define something known as an eye or a camera or a viewpoint that's looking at the object. So in case of a rectangle, you're always looking at it from the front, and there is no concept of depth. You cannot really move around it. So we really don't need a specific eye to look at it or a viewpoint to look at it. But with 3D objects, we could be looking at that object from multiple angles. We could be looking at it from any angle that I wish to. So like in the real world, when you're interacting with 3D objects, you could actually go behind a room and look at it, but you can't really do that with a 2D object. So when we are working with 3D, there is an important concept of a camera or a viewpoint that comes into play, and essentially this camera or a viewpoint is also nothing but it's just a mathematical calculation. So you really don't have to remember how that mathematical calculation works, but when you're writing a shader for yourself, you would have to understand how that calculation works, so you can really simulate that calculation using a shader. Now, what you see on the screen right now is likely the most complicated slide that I have, and it's so complicated that at times I cannot figure out what I wrote. But this is the most complicated slide. I mean, this is the crux of how 3D gets converted into 2D. So the way we can look at it is that the easiest way to figure out how a 3D objects get converted into 2D space is by understanding how a camera works. And the graphics that I've used here is probably from a book that's about what 25 years old now. So this is not really a new concept. It's a very old concept, but it keeps coming back. So let us really imagine, when we talk about the graphics pipeline or the conversion of 3D coordinates into 2D coordinates, we essentially talk about 4 sets of data. The first set of data essentially is known as the world data. A world. So if you look at the traditional analogy of a camera looking at a model, and let me just actually pick up a model to show you how things work. So maybe I have an object in front of me, which is this eraser. Now imagine that this eraser being looked at by a camera. So the actual coordinates of this, the coordinates that you see on the left, imagine this is the cube that you see on the left hand side. This essentially has 6 vertices, and each of them has a number associated with it, which tells us where in the world is this entire thing kept. Now this particular object could be either kept like this, or this particular object could be rotated and kept like this. Now when that happens, if you closely notice, if this was in this orientation and we change the orientation to something else, the actual numbers on the vertices changed. This is what we typically call as a world coordinate. So every object in your scene, in your game, has a world coordinate, and that world coordinate defines where is your where is your object in 3D space. Now the real fun happens is when you could actually also change the position of the camera. So let us say you're looking at this object at this angle, and it resembles a cube that you see on the left hand side. Now if I change the position of the camera, so let us say I change the position of the camera to something else, when I do this, you would realize that the vertex actually moved away virtually, and the vertex, when it moved away virtually, is what, when that happens, the new set of vertices that we get, sorry, I think I went out of scope. So the new set of vertices that you get is now called the view coordinates. So what you've done is that your object hasn't moved, but your camera moved. When your camera moved, it tried to look behind the object, or it tried to look at the object from a different angle. You never really changed the world coordinates of the object, but you still changed the actual coordinates of the object, because the camera moved. So the object was still at the same location in the world, but just because you moved the camera, you still had to apply that transformation onto that object. And once you did that, what you get is known as, so your starting coordinates. So let us say your camera was at 0, 0, 0, and the point C was a 440. You move the camera to a different location. Now your object still remains there, but what happens is that you come up with a new set of vertices, which essentially have the camera transformation applied onto it. So while your object still remains at the same place in the world, you still have to change the vertices of that object. This in our parlance, in the gaming parlance, known as a view transform. Once that happens, the third step is that, and the third step is where actually the 3D gets converted into 2D. So you have a 3D set of vertices on that cube, but there is a mathematical procedure known as the projection. What the projection essentially does is the projection actually looks at those 3D vertices and tries to it basically tries to flatten out each vertex onto a screen. So when each vertex in this 3D object gets flattened onto a screen behind it, what you get is a picture on the 2D screen, which can actually now have 2D coordinates. So essentially, if there is an object like this, and there is a screen behind it, if you project each one of these items onto the screen, if you project each one of these vertices onto the screen, so when you do that, what you actually end up with is a plane is a plain area of the screen which is now 2D, and which essentially has the has the vertices converted into pixels. This is what we typically call as a projection transform. Once we do the projection transform, the final thing is the viewport transform, wherein we try to clip everything that's outside the view area, etc., etc. And what we finally get is a set of 2D vertices that we can render to the screen. So all in all, what really happens is that now if this cube has 8 vertices, then these 3 projections, the world view projection and the viewport, is going to be done on each of these vertices. So now imagine if you had a model which had 1,000 vertices, then you would actually be doing this for 1,000 vertices. And if you had 1,000 instances of that particular model, you would actually be doing it 1,000,000 times. This is how things become computationally expensive. And the way we achieve this quickly is by streaming all of this data to the GPU and then letting the GPU do all these calculations. GPUs are good at doing things that we want to do over and over again, but which do not have a lot of if conditions or a lot of checks around them. So GPUs are very good at doing things that sound dumb. You want to take a value, multiply it by 2, try doing it on a CPU and versus a GPU. A GPU is going to easily outrun the CPU doing that. So essentially, for each vertex, you want to carry out this entire mathematical calculation. Now, feel very lucky you don't have to do this all by yourself. This is typically done by the computer. This is typically done by all gaming engines. So all you need to do is you need to hint how to do this. Now, like I said, you only need to hint the GPU on how to do this, and you only need to tell the GPU how to do this. Since we discussed that, this is pretty much a very complicated operation, and each vertex could really have a lot of data around it. You just don't need the position. There could be the color data, there could be the normal data, there could be a lot of other data that comes with the vertex. So vertex might not just be the position in 3D space, it could have a lot of other data with it. Now, typically what happens is that all of this capability is built inside your GPU. So if you're using any GPU, even if you're using the most basic GPU, even if you're using an onboard GPU right now on your machines, it typically has all of this built into it. And the way it is built in your GPU is something we call the graphics pipeline. So essentially what happens is that all this conversion of 3D into 2D, which is known as vertex processing and clipping and projections, is typically done by the GPU. You tell the GPU how to do this, and then you give it a large set of data, and it will continuously keep on repeating that particular algorithm on that data, and that's how you get and that's how things get converted into the 2D space. Once they get converted into the 2D space, the GPU runs a process called tessellation, in which it calculates the triangles between those points. Once it gets those triangles, it goes into the pixel processing stage, wherein the final color of the pixel is determined, and that gets sent to your frame buffer. The moment it gets sent to your frame buffer, you start seeing it on the screen. So that essentially is the graphics pipeline for you in a nutshell. If you go to the internet, if you search for graphics pipeline on Google, you would see a number of various definitions around it, various implementations around it. However, the basic steps of the graphics pipeline still remain the same. Now, typically, if you go back 20 years into time, when graphics cards came in, and when graphics cards were good, or when graphics cards were just introduced, all of this was being done in the hardware of the graphics card. And the first graphics card that was ever able to do that was 3dFX Voodoo, so which was known as the first true 3D graphics card, and it had this entire concept of doing everything on hardware. So the hardware was actually responsible for doing all this vertex processing, multiplying things around, then doing all the clipping, then doing all the tessellation, and then finally giving the pixel the color, and then finally rendering. Now, at that time, DirectX and OpenGL were in their best years, and all of this was available to us via. So this was basically hardwired in our GPU. So the GPU knew how to do it, and all DirectX and our 3D libraries could do was to actually send that data to the graphics card, and then let the graphics card do all its magic, convert all of those pixels into 2D, and then do all the pixel processing on it, and finally render it on the screen. But as we progressed, and as we wanted better graphics, we wanted better things to be done. And new technologies emerged. And one of this new technology, which was the most important, was the programmable function pipeline. So what the graphics card vendors actually did was that they said that we are going to retain how the graphics card works, but we are going to allow you more control around the vertex processing, on how the vertex gets processed, and on the pixel processing, on how the pixel gets processed. Essentially, we could use we could you could actually write a small program which we call a shader that could get compiled and stored on the GPU, and then the GPU would follow, instead of following whatever it was doing earlier, it would follow your logic to do that calculation. And then we would still run it through the basic pipeline. We would still tessellate it like it happens, and then when it comes to the pixel processing stage, you could also give the GPU another program which is called a pixel shader, and then instead of the GPU running its basic logic, it would actually run your program to carry out the pixel calculations. A pixel shader essentially is only responsible for giving the pixel a particular color. So if you go back to our slide of where we were doing, where we were lighting up the bulbs, this component essentially finally tells the system whether that bulb is going to be on or it is going to be off. And once you have the frame buffer ready somewhere here, that is sent to the rendering engine, which actually does all the flipping and all the swapping and runs it in real time so that you start seeing that animation. Almost all graphics today, including even if you go with a basic onboard card, has all this capability. Of course, as you get expensive cards, or as you get better cards, they really allow you a lot of more control over the way this thing happens. But every basic card that you get in the market today allows you to write a basic vertex shader, a basic pixel shader that you can load onto the GPU and then give it a lot of data to work against. So this is really where I will really cut off, and where I will talk about where I will let Videep take over, and he's going to help us write this vertex shader in real time. So he's going to boot up a new screen, and he's going to boot up an instance of Unity, and he's going to start writing a vertex shader and a pixel shader and show you how they come together and how that is sent through the pipeline. So thank you for bearing with me for so long. And I hope I tried to make. I hope I was able to make some concepts easy for you to understand. All right, Videep, off to you.
I hope I'm audible now. Okay, I was pretty much on mute. Am I audible? All right, awesome. Okay, so I was just saying that I hope now we have a basic understanding of how 3D data is then pushed on from the CPU to the GPU, and how it is processed in a programmable function pipeline. Okay, so because we follow a data flow model, right? We just take certain data from the pipeline, modify it, and push it forward for the next stage. That's it. That is all about basic programmable function pipeline. Okay, we have a data flow model, we take the input, we modify it and pass it on to the next stage. Now let's start off with the very first slide. CG basically, if you must have ever opened up or tried writing your own shaders in Unity, right? You might have come across two keywords, CG program and end CG. Okay, so these two keywords suggest that Unity is using a CG compiler which takes in a CG program, compiles it and converts into a shader code that is then executed by your specific GPU on that particular platform. So be it OpenGL, DirectX, whatever platform it is, it will compute on that. All right. So when we see the words CG program and endCG and we assume that we are writing a CG file or a CG program or a CG shader, it means we should refer to what NVIDIA created with Microsoft. So CG basically is a language that stands for C for graphics that NVIDIA and Microsoft in a close collaboration developed. Okay, so Microsoft then named it to HLSL because high level shading language. All right, and NVIDIA kept the CG implementation with itself, and it thought that it can convert the code into OpenGL, DirectX, or various platforms. So if you ever want to see the graphics APIs that you can work on with CG, do refer to the NVIDIA's developer zone. It is a very good documentation. All right. Moving next, because CG supports OpenGL and HLSL, that means the developers can independently write the code without worrying about any of the graphics APIs, application programming interfaces. Okay, that means I as a developer now use CG, write a CG shader and compile it using a CG compiler, and it can be rendered on a Mac, it can be rendered on a Windows or a Xbox or PlayStation. That is why Unity supports so many platforms. That's great. So that's it. Next up, we have to understand one important thing, that as CG is a language, okay, NVIDIA got the CG compiler so that it can compile the code offline or at runtime. If you must have ever opened up the your Unity window, and if you would have gone into the play mode and then changed the shader, it compiles directly at runtime. So that's the magic. And finally, we have to understand that it follows the data flow model, which means we are not changing the data that comes as it is in the same structures, but we have a pipeline already defined. We just swap certain things, modify the data and pass it on. Okay. Now let's take a close look at how CG fits inside your application. Like we already mentioned multiple times earlier, that you have to have a CG compiler. So let's say tomorrow you are writing your own application, a 3D application. You want to support DirectX and OpenGL, right? You have to make sure that you integrate the CG compiler if you are supporting the CG shaders. That means then you would be able to compute the shaders on all these platforms, be it PlayStation, Xbox, your Mac, your mobile platforms, because CG compiler at the background compiles it either offline or at runtime. Okay. Why we are discussing CG is because the major code that we are going to write, or the pipeline that we are going to change or modify, is going to be a CG program, and hence being a language, let's take a look at what it supports and what it does not support. So the CG shader or the CG language, right, that we are going to write, it has the core syntax which is similar to HLSL because Microsoft and NVIDIA both in collaboration made it, right? So that means you would be fairly comfortable in writing HLSL code. Okay. It supports 6 basic data types, which is float, half, int, fixed, bool, and sampler. Now here float would be 32-bit, fixed would be something like 8 or 12-bit, half would be 16, so something like that. You can refer to the documentation always. Excuse me if I'm not much correct here, but this is how it usually goes. Sampler is basically when you want to use textures. Okay, so if you want to use textures, you use a sampler, and that will actually extract all the data from your image or a texture. Now we will not use this word image, we will always use the word texture. Then a couple of things that it supports is your vectors in a form of float 3. In Unity you write vector 3, vector 4. Here you write float 3, float 4. In matrices it supports 3 by 3 matrix, 4 by 4 matrix, and so on. Structures, arrays are very important. Structures are very important because we are going to write a data structures and we are going to take the data and replace the data. Then we have, see, any language would definitely, when it is getting compiled, would like to be controlled, or there should be a flow control for that language, right? Otherwise all the lines will be executed, even which are not necessary. That means it can support if then else statements, it can support for loop, while loop, and of course basically it will definitely support function calls, right? It does support a lot of arithmetic operators. I have not written them here, but a couple of them are supported. After that, they are like plus, multiply, and etc. etc. Okay. Semantics is a big thing that we need to understand because graphics works on semantics as well to identify what kind of information you are passing. Okay. So I would definitely recommend you, I'm going to share this link with you. Do read this document on semantics. We are going to talk about it in detail in the upcoming sessions because this is basic. I will give you a basic idea. Semantics is basically telling the GPU that you should expect this kind of data. Okay, let's make it very simple. If you are using Vertex, okay, passing on Vertex information, say that GPU, there's a positional information I'm passing on. If you're using normals, say normal information. UVs would be saved in texture coordinates. Then any kind of information that you are taking in as an input and passing it to the next stage. That semantic is a way to identify for the GPU to identify what the data is and where is it coming from. It's basically you're tracking that information. And it supports the preprocessor directives. I will come back to this preprocessor directive when we are writing the code. Because when we write the preprocessor directives, it means we are saying or assigning a particular function or saying that, okay, for a vertex function example, use this kind of function. So we are giving it a reference to that. Okay, we will come to that when we are writing our shader in the next few slides. Okay. Now, as a language, again, okay, what we have to understand is like what we can do in this, what we cannot do in this. So, C for graphics based on C, simple, can be compiled offline. We saw that earlier. It does not support classes and objects. Okay, so don't write classes and objects. It may give you errors. Then input output operations. Now you will say, why do we have includes? Okay, so includes is before compile time, okay, compilation, and at runtime, input output operations, writing files, reading files, not allowed. Standard library for various graphics, yes, this is the standard library I was talking about. Go through this. I'm going to share the link with you. Let me share it right now itself, so that you already have the data in the chat. Awesome. And then one interesting thing that we will use later on, but not now, which is reflection vectors. We have a function for reflection vectors, which means if you want to do some calculations on the incident ray and the reflected ray and all that stuff, that you just have to call a function for. Okay, so no need to do some mathematics. CG is like pretty much capable of that. And that said, okay, whenever we have to execute or process multiple pixels at the same time, right? You can be rest assured that this will be run parallelly in relative isolation. That means there will be no dependability, and hence it will not cause any errors or throw any execution errors. Okay. And the last thing is, like as NVIDIA says itself, that it can be limited due to the limitations of GPU. That is okay. If your GPU does not support something, it just does not support something. I cannot just run ray tracing, on a non-ray tracing supported GPU. So it's pretty much simple and straightforward. Now that we know that we have to basically write the CG program, okay, We have to write the CG shader. We don't have to write the CG effects. It's just a CG program that we have to write. Okay, let's see what goes inside it. So these two words are the keywords I was talking about earlier: CG program and NCG. Okay, when we say CG program, it means that your program is starting. When we say NCG, it ends there. Your preprocessor directive here says that GPU, okay, not basically the GPU, but the compiler, you have to assign simple vertex function. This is a name or a string that we have written, okay, and assign it to the vertex shader or the vertex function. Similarly, for the fragment function, we do the same thing. We can give any string possible and assign it to the fragment function. Okay. Next thing is to follow the data flow model. That means fetch the data which is available. So we are fetching the data here in a structure. This structure contains a vertex information. Now vertex information will be position of that particular vertex in object space. That means relative to that specific object. Okay, it is of type float 4. So we define that in a structure. Then we say we have one structure, but we cannot modify the same structure. Okay, so we make one more structure similar to the same thing like the previous one, and in that we say that this structure, okay, will have the same vertex information, but we are going to write into this. All right, and then we go on writing our vertex and fragment function. So when we write our own vertex function, we have to modify the vertex if required. Okay, usually in vertex function what we do is we take the object space vertices and then just apply the projection matrix to make it or convert into a clip space. So that means your vertex position now goes from 3D to 2D swap mapped on a screen, and then we go to the fragment function. Now a very important thing to understand is a pixel can have multiple fragments, okay, because there are multiple shaders. Multiple shaders will have multiple fragment functions, or one shader will have multiple passes that will have multiple fragment functions. So a pixel will or may always have multiple fragments, and your shader will define what color to write to it. Now there are a couple of other things like depth that we can write on the fragment, but for now, as it is basic, we have to focus on putting out a color. So it's very simple. You start a CG program, you define your vertex and fragment shaders, you take the input, you provide a structure for modified input, you modify the input in the vertex function, pass it on to the fragment function, just as the pipeline we had seen when Girish was presenting. Okay, and then in the fragment function we finally say that this pixel would be, no, this fragment would be of this color. Pixel would be defined later on. Okay, and then we end the CG program. That said, we have not yet come to the point where we have to write this into Unity. Okay, so if you take this code directly, you will be able to write this into Unity. But how? That's a good question. ShaderLab. When we say you are writing your own application, suppose Unity, which has a CG compiler, which has a CG program, how are you enabling this mapping between your CG compiler, your CG program, your artist who is actually having a material in which a shader is attached, and changing the properties? How do you do that? So ShaderLab is something that Unity uses, and it's basically a declarative language which just wraps up all your code in a presentable manner, and your Unity just executes it, parses it and executes it. All right, so that's just pretty much simple. Now, when I say that's pretty much simple, we have to take a look at the ShaderLab syntax. Okay, so basically it has what do we say? Couple of blocks like property blocks. It has tags. It basically being a declarative language means it will have commands. Correct. So you have your shader, which has properties. These properties are exposed in a material so that the artist can also tweak them. These are exposed via script so that developers who don't know shader writing can access those properties and change it at runtime. It contains tags. Now tags is like, how do you want the render queue to be? Do you want it to be geometry? Do you want it to be transparent? Now transparent shaders will always be queued after your opaque shaders. Why? Because For a transparency to render, if it is kept in front of an opaque object and you render the opaque object in front of it, it will not give you the correct output. So simple, transparency has to be rendered at the very end. Then it has a couple of commands we will definitely talk. Then it consists of subshader. Now subshader concept is important because when you're writing a shader and suppose it is not uh, you know it is not being rendered or supported on a specific platform, then you write multiple subshaders saying that okay, if ray tracing is not available here, I'll write a subshader which will allow some kind of an effect which is similar to that ray traced effect. Okay, so you support multiple platforms like Xbox PS using subshaders, you support multiple graphics cards using subshaders, and that is where you write multiple subshaders. Okay, then it consists of passes. Okay, now this is where your CG program will go. When you saw the CG program earlier, right, the CG program was basically a piece of programmable function pipeline modification that goes inside a pass. Okay, let's understand it like this. So you now know how to write a CG program. You just have to take that piece of code and write it inside a pass. And the best part about this is you can have multiple passes that you can blend. Let's say you write a pass which outputs red color, you write another pass which outputs green color. Then you do a blending operation like this blend command. Okay, it will, depending on the blend operation that you're doing, let's say addition, it will make it yellow. As simple as that. So simple. So you can write multiple passes. A very basic example of such kind of a shader is blur shader. When you have to do a horizontal blur, take the output, do a vertical blur, and then pass it on. Okay, and then finally, of course, your shader code is written here, and the main part is if by chance nothing works out, okay, then you provide a fallback to the shader. All right, now here we are going to quickly take a look at the syntax. I think we discussed that. So we have a shader command and the name of the shader. Then we have a couple of properties exposed by material to the developer or user. Then we have blending commands, we have tags, we have lots of other commands like LOD, level of detail, culling, if you want to do a backspace color or not, z-test, that means you want to always render in front. If you give a z-test value of always, it will always render on top of whatever objects you have. Then you want to make z-write, which means you want the information to be written on the depth buffer. We will all cover all these topics later on because it's a very big topic. Fog again, it is basically, should Unity consider this shader that is applied on that specific object, which means that object itself to be a part of the fog compilation or not. Then we have a pass in which you have your simple shader CG program, shader code, and a fallback shader. That's it. That is it. And when I say that we are going to just write this, what we are going to do is we are going to write our own Unity shader. So just give me a second and let me pull up the Unity window. Okay. All right. So I'm just going to quickly switch off the camera here. I'm going to go here and I'm going to share this window right here. All right. So one thing that I would like to share with you is we have a GitHub repository and you can download the code of what we are going to do. I'm just going to share that on chat with you right now. So here it goes on chat. All right, perfect. Now that said, let's quickly get on to some shading part. So we have a very simple basic Unity project setup here, and we are going to write a shader. So that means we are going to program the pipeline. Okay. So we are going to write a programmable pipeline, and it's a very basic simple which has an intro folder. It has scenes, which basically does not consist of anything, and we are going to start off with the intro. Also, do remember that when I have shared the GitHub repository with you, it is on the main branch. Please switch the branch to intro. Only then you will be able to see this. So let's go to intro, and you know what I'm going to do? I'm going to start writing the shader. Okay, how to do that? So first of all, I'm just going to make a new folder here, say live coding. All right, how to create a shader? Now we know ShaderLab syntax, we know ShaderLab. So what you can do is simply right click, create shader, and you can say I want to create an unlit shader. So just name it as a simple shader. I'll just add live. Okay, that's the name of the shader. When you open the shader, right, you get to see a lot of things, but now you are familiar. Now tell me if you're familiar or not. You have a shader command. That ShaderLab will understand that, okay, I have a shader of this name. You have properties that you can actually see it in the material window. Okay, and then you have a sub shader which has tags, one more LOD command that we have not discussed, but the command is there. You have a pass. The pass has the perfect shader code in it. Sorted. It has the shader code, and when you say you have your vertex fragment functions, then you have a structure to input the data, to say that I want this kind of data in the shader. You have a structure where the modified data resides. You have a vertex function that will modify your vertices, and you have, now I'm just, because it's a live coding class, I'm going to delete this. Okay, I'm just going to delete this. I'm going to save this and go to Unity. So Unity says that we have a shader, and I'm going to create a new material here. In the material, I'm going to attach this shader, and that's great. We have a pink colored, a failed shader. Okay, that is fine. That is perfectly fine, because it's not a suffix shader, it's not a fixed function, and there is no code to compile. Now, it's funny, like if there is no code to compile, what will Unity compile, right? That means we have to start writing our own code. So assume we saw the syntax. The first thing that comes up is properties, but we don't want to write any properties, so we can leave it blank. What next is important? Subshader. This is important, right? If you see your earlier slides, your subshader is important. Just give me 1 second. Awesome. Now what we have to do is, this subshader will have couple of commands like your tags or your LOD and all. We are going to skip that. Okay, I'm just going to say you write a pass. Okay, I'm just doing this so that, you know, when you start writing your shader, you would know what is important, what is not important. All right, so this is very important. CG program, and this is very important. Okay, if I save this here and you just want to quickly look what happens, I'm going to go to Unity and check. Here we go. There is some kind of code written, but there are compilation errors. All right, so you select the live shader sample here, which is in the live simple shader. I'm going to apply this to the cube. Okay, so let me check. It is pink. Okay, it is pink. Perfect. It says no surface, no fixed function. There is some code which, you know, is giving some compilation error, which means we can read this. Shader is not supported on this GPU. Okay. Secondly, vertex and fragment programs must be present. Now that you know this much data from our previous slides, you can actually debug the shader, which means we say that we want to have a vertex function. Okay, and now I can write anything. Okay, and this is very bad idea to name it like this, but just for the sake of the live class, I'm just saying I can write any name here. Okay, I can write a movie name also, which is a very bad coding practice. Don't write that. All right. Now, how do you write your vertex function? Simple. Simple writing of function. Void vertex. Okay. This is the way you write your function. That's it. Simple. Nothing has changed. But vertex function has to provide an output. Okay. So we have to replace this with an output. Alright. So we can just for the temporary purpose say we are going to write output here, and it has to take some input. That is also very important. So let's define where the inputs and outputs come from. So we have to define structures. Okay. I will share the link for this also. There is a beautiful Unity document. Please read that. Now in this particular structure, I'm going to write we need position. I'm just going to go very basic. Okay. So name of the structure is app data. What we want is from the input, what we are getting as an input is a vertex 4, vector 4, basically a float 4, which is called, you can call it anything, vpos position. This is the input structure, right? Now I'm going to write the output structure because we have to save something, right? Usually this function is called v2f, but this is not the function. Usually, sorry, I was going pretty fast. Usually this structure is called v2f because it goes from vertex to fragment, but we can call it anything. Following some, at least some little bit of coding, we can write vertex output. Okay, don't judge me on that. Now we have to take this, modify the position, and then provide it. Okay, but now what happens if we don't do that? Simple. Let's check this. What happens if we don't do that? First of all, we have to provide an output, which is going to be output. The function has to provide an output. So basic syntax. Okay, and this has to take your app data as an input. All right. I hope you understand what we are trying to do here. Okay. Now when I said that we have to use semantics, it's very important. Here we have, this is the way that the GPU is going to identify that, if I change the name of the variable here, GPU will identify that we are transferring some positional data by taking it from an input structure, and it is going to be transferred from vertex to fragment. But it's a positional data, and it is mapped to vpos when we are taking it as an input, and is mapped to vert when we are putting it as an output. Okay. All right. Now that done. Okay. We cannot directly use our structure like this. That means we have to put in app data. Let's say input. Sorry guys, I'm taking a bit of time, but I'm going to wrap it up as quick as possible. I'm going to show you a couple of more things because this is basic. This will take a bit of time more. Okay. Now we have a vertex function. In this vertex function, what we have to do is we have to initialize a structure saying output, or you can write anything. Okay. It is just the same how your programming languages work. Okay. You have to create a new variable. Then you say, let's do this. I'm going to say output dot vert is equal to input dot vpos. Okay, and I say return. That is it. So that we are returning back. Okay. Now we have to write a fragment function. See, if we don't write a fragment function, it will still give us an error. All right. So when we write a fragment function, it's going to be very simple. Here we just have to say that this is for the time being going to return a color. Now color will be of RGBA. So float 4, fixed 4, half 4. You define you want 32-bit, 16-bit, 8-bit, up to you. Your call. I'm going to say 32-bit. Okay. and I'm going to say this should be the name of the fragment shader. Here there are two things which are important. We have to take the data that has been passed or modified, which means we output structure. All right. This will be the input for this. So let's say we whatever. Now this is very important. This semantic will tell that wherever you're passing out the color, it has to have a rendered target in which it will be rendered out. Okay. Now I'm going to simply say return float for RGBA. That is it. Let me go to the Unity. Whoa, we have it rendered. Now see, if you see this live simple shader, it's very simple. Okay, it has compiled, and there are a couple of things here. We have a render queue also. If we select the object, we see there are no properties because we have kept the properties block empty. These are compiled by the Unity, so it's fine. Okay, render queue, we already have it. We have mentioned it. Basically, even if we have not, Unity will add as a render queue. But now you see there is a problem that we are just rendering the vertices as it is. There is nothing happening. Whenever you're moving the camera, this is not the cube that I wanted. But it is the cube that you wanted because that is how you have coded. Okay, that means when I code and I just give the position from the input structure and pass it on, that plane is what you see. The vertices are getting overlapped and it's just forming a rectangle, right? That means we are missing out on one very important step here, which is very simple. You have read about the programmable function pipeline that Girish just mentioned. Okay, in that you have a tessellation shader, vertex shader, geometry shader, you have a fragment shader, all those shaders. Okay, but where are you doing the matrix multiplication for converting from object space of that vertex to view space to your clip space? Where is that happening? That's not happening anywhere. So we have to make that happen now. And how do you make that happen? It's very, very simple. Okay. All that we have to do is Unity provides a basic function called Unity object to clip position. That means convert the position of that particular object from object space by applying a specific matrix to view space and then from view space by applying certain matrix to a clip space. So you must have heard about MVP, model view projection, that Girish just explained. So that is what we are going to apply. And then if I just go to Unity, whoa, we have our cube. How interesting is that? Just one small mistake of not understanding the graphics pipeline will give you a random shader. How cool was that? Okay, so not wasting time. I know it is not cool, but it is a mistake, all right? And everybody at some point of time will do it, or if not, if you want to check the matrices how they work, you can specifically do the matrix calculations here. Okay, so yeah, this shader, let me go to Unity once again. Sorry, I'm so sorry guys. This shader, live simple shader, is basically in your intro shaders, simple shader. This shader and the one that we have applied is the same. Now let's quickly, I don't want to just put a cap here. I know we are running out of time actually for this session, but let's quickly add some couple of things. Unity says that ShaderLab supports a couple of things like textures, it supports floats, it supports colors. Okay, so let's add a quick color to this. So I'm going to say a property called primary color. What's the ShaderLab syntax? Name of the variable, parenthesis basically. Okay, name that will be appearing in the material editor, which is I'm going to say color A. What is the type? The type is color. and then we have to assign it a default value, and default value here will be RGBA. We duplicate that. I'm going to write two colors. Secondary color, color B. Now you quickly go to Unity. Okay, I was sharing the wrong screen. I'm so sorry. I was sharing the wrong screen. Let me go over that again. Basically, it's very simple. When we write our properties, we say the property name, which is color. Okay. So variable name, the name that will be appearing to the user in the inspector or the material window, the type, and it's going to be color. Oh, sorry. We have to assign it a value which is RGBA. So RGBA. Similarly, secondary color, color B, and now we switch to Unity. And then we have this cube which has a simple light shader. We have two colors, and I'm going to make it red, and I'm going to make it final color is going to be yellow. Okay, so I'm going to make it green. No color changes. Why? Because very simple. We have said that we have variables which are in properties, but how does this pass get this information? Oh, it's very simple. We just say I want to return, instead of float 4, because this is float 4, primary color. Huh? That's what most of us will say. And when we transition to Unity, it says, oh, we got an error. And what that error is? Undeclared identifier. Okay, that means we have to somehow tell this pass to use that property. And how we are going to do that? In the CG program, we have to define it here. So float 4 primary color, and we transition to Unity, and the primary color is all here, red. Change it to whatever you want. Okay, so not wasting much time again. What do we do about the secondary color? Simple. Take it from there, float 4, and copy. Now we say add it here, and then because I wanted to specifically create yellow color, I just added both the colors. Okay, so you can just go to your shaders. You can select simple color. This is the same code that we have written now in the example. Third thing, very quickly, third thing. Okay, this is done. You can have multiple. Okay, you can have a sphere. You can just attach this, and we have a yellow sphere. It supports scaling also. Okay, now you're rendering. You are now a master at rendering colors. Okay, so colors, you just can quickly render it. All right, but now someone says that, oh yeah, why only color? I want to support a texture also. Okay, so you say, fine, that's fine. I have to see the Unity documentation for that. So you go to the Unity documentation. I'll provide the link, and then you provide a variable. Okay, you can provide any variable. So texture. From now on, we are going to call all the images as textures. Okay, that is what in the programming I'll do. Okay, what is the type? It is a 2D texture. Okay, now how I know? Because I've been programming shaders for a bit of a time. I know the types that are supported by ShaderLab in the properties block. Okay, and the values. So let's assume it's going to be default white, and oh, I have to just leave it empty. That's it. So your main texture is ready. Now your main texture is ready, so we can apply it. But here, I would like to take you back to this presentation that we were talking about here. We did our basic shaders, we did the properties, we did the texture mapping. Okay, we are doing the texture mapping. What I want you to understand here is, when we do the texture mapping, Okay, Unity will support 2D textures. You remember the word sampler, right? That CG supports. So it's a sampler 2D is a 2D texture. Sampler cube is your cube map. You remember when you have sky maps and you use cube maps. Cube maps is also supported. 3D textures are also supported in this. Okay, so you have your 2D cube and 3D texture, that is all sorted. But what is this, ST? So Unity will allow you to transfer the tiling and scaling data, okay, with that specific texture by using this keyword. So whenever you see a texture, let me quickly transition to the Unity, okay, because we have a property, right? Because we have a property here, we have a texture here, we have tiling and offset. All right, so instead of scaling, it's offset basically. So tiling and offset, and we have a texture here. All we need to do is we just have to map it. We have to take these 4 properties. So that's why that st will always be of type, just type it in the comment box. Will it be float, float 2, float 3, float 4? How will you fit in these values? Just type it in the comment box. Let's check. Okay, in the meanwhile, I'm just going to write alright. Now when we have to use this main texture, what we can do is we can quickly say uh, we can say it's a float 4 because texture is going to be RGBA. So float 4 texture value is equal to text 2D. Okay, this is a function by NVIDIA. Okay, now let me quickly check if you are actually viewing the code. Perfect. So now what we have done is, I don't know if you would have typed or not, but we have added or referred to that specific property main text here as a sampler 2D. It has a float 4 because it has tiling XY and scaling XY, basically offset XY. Okay, so it's a float 4. In the fragment function, we are using a text 2D function. Okay, we're creating a new variable, creating a text 2D function. Here we have to provide 2 things. We have to provide the texture and the UV mapping. How is the UV mapping done? Okay, so o.uv. Alright, now where does this UV come from? UV comes from the output structure, but does our output structure consist of UV? No. Why? Because our input does not say so. So what are we going to get? We will get a pink screen, a pink shader. That's it. Now let's quickly solve that. So now we want, or we are dependent on the UVs of that particular object, right? We will say we want float to UV. I'm just going to go very conventional with this standard. This is the semantic for the UV text code because it will give me the texture coordinates. Okay, and here we are going to learn one more thing, that output dot UV is going to be transform texture is a function of Unity's common includes, okay, standard library. It will transform the UV and make it show that your vertex specifically maps to that specific UV coordinate, and then we have to provide input dot UV. Once this is sorted, we are still going to get an error saying that where is this transform text coming from? You just write any function and you provide any variable to it, argument to it. So we have to remember that no, we don't write just anything. We have to include a standard library. Okay. Sorry, something went wrong, I guess, somewhere. Yeah, include I forgot the name of the library. It's basically very simple. Unity CG dot CGINC, I think that is the one. Now we will come to writing all these includes, but for now understand that we are calling a specific library or maybe a specific file. But CGINC is that CG, okay, include, that is the extension. We're calling a CG include kind of a file which will have this transform text function. So I think I have written the name wrong. I just 1 second. It has to be unity cg.cginc. And now let's quickly go and see what if it is right or if it is wrong. Okay, and it is wrong. It is completely wrong. Okay, so what does it say? It say not enough actual parameters. Oh, so there are no actual parameters for this. All right. Why? Because let me take the shader. Okay, not enough actual parameters for macro. Okay, transform text. Okay, so that means now at least one thing we are sure of is that our code is including the right file, our function is right, but the parameters are not correct. Okay, why the parameters are not correct is because when you read about this function and what all it takes in as in parameters or as arguments, you will find out that excuse me, it will have to map a certain texture to the UE. Okay, when you do the transform text, so this is where it will pick up your st values, like main text. If I give it here, now there is one more thing which is wrong that I'm deliberately going to show. Here we go. It says undeclared identifier main text underscore st. Now we are providing the main text here, but where is the scaling and tiling of it? It's not there, which means always remember that even if you write or define these variables here, the order should be correct. I can leave primary and secondary color here, but if we are utilizing these two before the vertex function, they have to be uh, right here before the vertex function. Okay, so now if you see, it works perfectly fine, and this is showing yellow color, your sphere and cube. I can give it a basic map saying something like this. Okay, and it's not just applying. Okay, so we'll just go and ask Unity the shader to apply. So when you have to apply it, you just have to say that instead of primary and secondary color, use a texture. There we go. We have the textures sorted. Okay, so we have the texture now. We have the colors now. One small thing is that in the shaders you will find this simple texture right here. Okay, that's the shader that is there. Use that shader. One small thing that I want to introduce you just now is that one little bit function called as lerp. This you can just enjoy. Basically, we will talk in detail about this in the next upcoming sessions. Lerp, basically what it will do is, if you see the current properties, and if you see the current map, it's a black and white map. Okay, so what we can quickly ask you to do is, just as a fun part, I'm just going to say lerp between the minimum and the maximum value using a specific value, okay, or time t, whatever it is. And here I'm going to simply replace lerp between the primary and secondary color using the texture. Now when you want to go or lerp between two float 4s using a float 4, it's not a good idea. You should lerp between a uniform value. So that means if I just do a red channel, because it's a black and white image, red, green, blue, alpha all will go with the black and white image itself. Okay, I think I did a mistake again by not sharing the code. I'm so sorry guys. Just uh, give me a second so that I can explain you the code also. Okay, so let me share the code now. If you are able to see the code, yep. So what we're going to do is we're going to write a lerp function where we're going to put the minimum value, maximum value, and the value to lerp between. So if this is 0, it will be primary color. Okay, you see that? If it is let's say 1, it's going to be secondary color. So you see that. Now if I give it a grayscale value, it will be a mixture of it. Okay, so 0.5, and if you just go here and check it out, it's a mixture of that. And that's why this lerp function is very useful, because now what I'm going to do is I'm going to lerp it between the texture values. So tx.red channel, alpha channel, all right, not alpha channel but the red channel, which will still give the basic lerping. So whenever you see this, all right, we have this cube. Wherever it is black, it is 0, the values are going to be red. Wherever it is transitioning into green, or sorry, white, the value is going to be green. So wherever it is completely white, you see green. So you can find this shader also here, which is called a simple texture shader. So sorry that I took so much of time, but I think now we are good to go. I wanted to cover vertex displacement also. Unfortunately, I was not able to do that. In the next class, we are surely going to talk about vertex displacement. Okay, how you can write your own shader, which is very simple. Okay, and displace it. Okay, that's something cool that we are going to do next class, next session, not class, not in classes. Here, all right. So, guys, I think that is all for today. It's been a very long session. I know. I'm sorry for that. It took a lot of time. But can you please, let us know if it was, uh, or did you understand the basic pipeline? Also, if you have any questions, please write them in the comment box. Great. Any questions that you have, or are there any questions like which are unanswered? Property name should be same in CG program. Yes, the property name, the variable name that you are providing in the property block has to be same in the CG program, because that is how it will refer that specific property from the properties block. So there should be, when Unity uses ShaderLab to nest or combine everything into a structure so that Unity can parse it, that is the way it should provide. Absolutely. Property name should be same. Can I know if the same way the shader has to be written for UI elements? Any idea on that? Yes, yes, absolutely. For UI elements, okay, like explained earlier by Girish sir, okay, everything that gets rendered on the screen, which goes to the GPU, right? Okay, your graphics that are getting rendered will follow a specific pipeline. Even if you're writing your UI elements, okay, they will follow a specific pipeline, and that is how it should be rendered. Okay, so if you are writing a sprite renderer, if you see a sprite renderer, you have sprites, right? They also have a specific shader attached to that. Okay, so if you want to be specific about certain UI shader, you can just drop in a question on the specific UI shader. We can cover it up. We can definitely explain. But the pipeline has to be followed for the graphics to be rendered on your screen. Any must-read book for a shader developer? Yes. Before you read any book, the best thing to read is the manual. There is a great manual by Unity. Okay, so do read this app. I'm just sending it to you here in the chat box so that everybody can see that. There are there is lots and lots of material basically. So if you go to example section also, you can just read all these examples. It's very helpful. Apart from that, Girish sir, would you like to recommend certain book? I think Girish sir, you're on mute. Your voice is not audible. Okay, so Jasmine, just to quickly answer that question, if we really want to go through a book, right, you want to first understand the graphics pipeline. You feel comfortable with OpenGL, go with that. You feel comfortable with DirectX, go with that. It's basically we are writing a programmable function pipeline in which we are modifying the pipeline itself by using your tessellation shaders, your vertex shaders, your geometry shaders, your fragment shaders, your domain shader, hull shader, etc., etc., etc. So there are so many shaders that you have to tweak if you want to write a full-fledged shader program. You can read any book, OpenGL or DirectX. I would check out if there are some good books on that, but read that. Okay. Next question. You use underscore before the main text property. Is that how it should be declared? No, not required. Not at all. Not at all. Just 1 second. Did I use underscore? No, no, I haven't used underscore in front of the main texture. So if I will show you the screen again, uh, here. So I have not used underscore. There is no convention for using textures like that. Basically, it's a variable name. Unity follows that underscore naming convention. You can definitely do that. Not an issue. But yeah, we don't need to write underscores. Okay. Apart from that, textures basically, they have a couple of other parameters, some functions like these, and this we will discuss in detail. There are a couple of more variables that you can declare. For scaling and the tiling part, you can use this one. Okay, that said, okay, so Greaser has recommended Frank D. Luna for graphics pipeline. I think it's for DirectX. See, shader graph, node-based versus shader scripting, which is better in Unity? Yes, very good question. Which is better in Unity? Depends on your purpose. Okay, it completely depends on your purpose. When I was working with Girish sir in Gurgaon, we were challenged basically to get a beautiful rendering output. Okay, for one of the stadiums in Miami and Red Wings, that we had to write our own custom shader. That time shader graph was also not available. Okay, now I don't specifically know if there is an option to write tessellation shaders, or how you can, I know you can access the depth buffer, but how you can access various things. If your aim is to write specific functionality in a shader which does not require you to get into the core graphics API, please go ahead and write shader graph. It's very friendly, it's very useful. And if you are just looking out to write shaders for some effects that can be quickly achieved on objects, go ahead and use shader graph. It's really good. Okay, so yeah, these days basically people are using a lot of shader graph because what's happening is uh, when it comes to node based, you have a visual reference, and when it's a visual reference, you have that ease of understanding and linking things together. Like, okay, this is what I do, this is what I get, and what you see is what you get. Basically, happens in the shader editor itself. So it's perfectly fine to use shader graph. If you really want to get into some more detail where you want to maybe use some ray tracing functions that are in the shader model 5, or if you want to use tessellation functions, write your own geometry functions, um, displace vertex with some specific things. I think vertex displacement might be possible in shader graph, maybe. But yeah, and if you are anyways trying to ever switch from Unity or to other graphic software or make your own graphic software, go ahead. Absolutely. So this is pretty interesting. We had also worked on a WebGL project in which we wrote our own custom shaders. So that was pure WebGL. Okay, and when we wrote that, we had our own custom shaders, and we were doing runtime pixel manipulations on a 3D object using multiple layers of textures. So that is one interesting use case where you have a plain object, okay, and based on your cursor position, you can quickly go ahead and just you know do some shader operations, perform some pixel operations in a fragment shader using the mouse input, and you can quickly change or do a lot of pixel operations to show multiple layers of textures and perform and in different combinations basically. And it's very dynamic. Shaders are very dynamic. You know what the best part of shaders is? I will tell you. You can design screen space effects, you can design object effects, you can object basically the 3D object, you can do a lot of particle effects. It's just amazing. You can do particle effects in that. That means you also have an option to define a null object or a null mesh with zero vertices, okay, and then dynamically generate the vertices and let the processor compute. Then you have compute shaded. You can do physics calculations using shaders. Right? They are super fast. If you must have heard about compute shaders, physics operations are amazing. Okay, so yeah, there are a lot of things. We are going to put this video live on YouTube. I don't know if you have been able to go through this channel, but uh, if you really want to start off coding shaders, we have a channel here. Feel free to subscribe, or just subscribe if you like it. Okay, don't subscribe just for it. Subscribe if you like it, if you want to really learn it, and you can see some really good effects like this one. I can just quickly play some kind of a this is a screen space effect. So all the pixel operations happen in a fragment shader on a screen space level. All right, and then this is an object effect. Basically, if you see this kind of an effect, it's done on the objects. Okay, so you can just go and paint on objects. That's in a shader. That's so quick. Then you have one more. There are so many things that we can still discuss, like stencil test, this, that. So some cool stuff, some really cool stuff that you can do using shaders. Cool. Any further questions, guys? Awesome. So I think Girish sir, do you want to add something? Okay, so next session we will do it quick. Definitely, we'll do it a bit quickly. We will show vertex displacement because I think modifying some vertex shaders is what you might want to really look at. And then progressively, we are going to cover more topics. Definitely, we'll go a bit in depth. Uh, I will definitely share form to just get a feedback how it was, how it went completely, and. Do sign up on the meetup page, guys. There is a meetup page that I have shared the link with you all. Please do sign up on that so that whenever we have meetups, and let us know if you are up for some coffee meetups. Just if you want to do your own shader work uh, and you have downloaded this code from this repository and you're trying something, we can have a coffee meetup every alternate weekend or every other weekend, basically, to just see if you are stuck somewhere or not. Awesome. So we already have a feedback form. That's super cool. I would request you all to please go to the feedback form and just. Okay, I need some permission. Maybe you will have to tweak Girish, sir. That we will update the feedback form and send it out. Okay. I hope you all liked the session. It was a very first session for me and Girish sir, and not Girish sir, but for me in collaboration with Girish sir. Uh, do let us know in the comments, please. That will be really helpful. All right, then. Thank you so much for joining in. Okay, let there be some light. It's just going to be dark. Yep, I can access the form now. So, yes, here we are. We have a feedback form right here ready. And guys, please fill in the form. Curvy world effect like Subway Surfer. Definitely do send us the shader, not the shader, but the video or some kind of a clip, and we will definitely take a look into that. We will make a tutorial on that for sure. Thank you so much. Thank you all, and please fill in the form, the feedback form. We'll look forward to your support because uh, the more you motivate us or encourage us, yeah, it will be helpful for us also to make the videos going and sessions going. I hope you will create some shaders using this code, and please do provide a feedback. Thank you so much for joining us. And thank you, Yuri sir. Thank you.